the nice introduction. Actually, I am Dean of School of Technology here. I took over last year in the month of November. This month only around 25th of last year. So 24th of this month, I'll be completing my 1 year of service as a Dean here in the School of Technology, Nehru. So since Swarnivar has given me permission, actually Swarnivar and both of us are from the same institute, Neris. He also passed out from Neris, so I also passed out from Neris, and later on he worked there. He was fortunate to work there before shifting to Tripura University. So without doing much, this one, I think I should start the topic. However, if there is any comments or any, confusion in my talk, during my talk, please let me know. So, am I audible? Is microphone okay? Is my microphone okay?
Sir, you are audible, sir.
Okay, thanks a lot. Let me lock my window also. Okay, so now actually few weeks ago, Swarnivar told me that I should deliver a talk. So, and I asked him the background of the audience, and it's a kind of mix-up, right, Swarnivar?
Yes, sir. Yes, sir.
So, okay, yeah. Before then, in that case, before I start, because based on that, I think I can move or play a little bit to make things easier for the audience to understand whatever I'm saying. So, may I know the field of department of all the participants, from which field you are from? I am from electronics. And what I'll be talking about is actually the part or the tools of the digital signal processing. It's on Fourier Transform only. So
Participants can put their field, which means whether you are from physics, mathematics, electronics, IT, you can put up. If you are unable to use your mic, you can put in the comment section also.
it will be easier for me when I say or when I explain. Accordingly, I'll shape my explanation. So one IT, one ECE, electrical. Okay, I think ECIT electrical. Yeah, ECIT electrical. I think most of you are from ECIT electrical, so I think there wouldn't be any problem. So you all are aware of the basics of Fourier transform, right? You can use your
mic. From
mic.
mathematics and physics also, they will be joining, I guess.
Okay. So mathematics, there wouldn't be any problem because they would know actually Fourier transform. Only thing that little bit difference would be there is that ours is a little bit application oriented and there is more of analytic. So that would be the only difference. Because in engineering, what we do is we use applied mathematics, right?
Yes, sir.
And whereas the this one mathematics, they normally do the analytic part only. So here I will not be able to touch that analytic part. Of course, analytic part, if we have to do, there is a whole derivation that we have. And I had been teaching also in my MTech students as an advanced digital signal processing. Thank you. Yeah, tomorrow we have AC meeting. Yeah. So what I'll be talking today is a little bit of, so you please feel free to interrupt me anytime. And I actually have a little bit of apprehension earlier that see the audience or even including me, or maybe I may be the only one who missed this out. So we had been using this Fourier transform, yeah, and its application in actually digital signal processing, yeah, the signal system for quite long time, and we really, we really don't do this part. This part means here in the subtitle I have given obtaining the imaginary part of DTFT, discrete time for a transform, from its real part, yeah, otherwise vice versa. Say now, suppose, say if we have actually, if you remember correctly, this Fourier transform, this DTFT, discrete time Fourier transform. So this discrete time Fourier transform, actually, this is a complex number. So since it's a complex number, we know that when we express them in rectangular format, so it has got a real part, and another component is the imaginary part. And this also can be expressed in magnitude and the phase form also. But what I would be concentrating here is actually, as I said, that's why the title or the topic of today's talk is on, I just gave it like this, the playing with DTFT of xn. So here what I will be doing is, or what we'll be seeing here is, say we have a one part of the Fourier transform, and we would like to, recover the complete DTFT. Say we have either the real part of this, yeah, otherwise imaginary part of this DTFT, and what I would be telling you is how how do we, what do we do to get the complete DTFT. So that is what I would be stressing today. So if you have seen earlier, or if there is any teacher or students here who had already experienced this, please let me know. Or if you have not came across these ideas, then it would be good for me also. And you please, if you have any doubt in between my explanation, so you please interrupt me. There are two ways to do it. One is analytic, as I said, from the mathematical point of view, using integration. And another one is, without using mathematical analytic, we can, exploit the real and imaginary, the sequence, or what we should say is odd or even sequence, odd and even part of the sequence. We can use, we can exploit that property, and then we can, get the one part from the other part. So we'll be seeing that. So here I just give a brief introduction of Fourier transform. So in Fourier transform, what we do is we actually normally require the complete knowledge of both real and imaginary part whenever we talk about the Fourier transform. So here the issue is we have one part of it. We don't. So we see our requirement is the complete knowledge of both these. But say now in a given condition that you have only one part, so how to get the other part? So that's the idea actually. So here again, yeah, I'll be avoiding this mathematical analytic approach. So we'll be exploiting the real and imaginary parts of the Fourier transform. And here we will see the odd and even component of the sequence. That is what we would be using extensively here. So while doing this, we would need actually two properties. We'll be using the two properties of Fourier transform. So the first property is, see now here we're going to use the the conjugate symmetric part of this xn. Xn is the sequence that we know. So here this conjugate symmetric part is normally that we because this portion, what I am saying, is from the point of view of complex numbers, yeah, otherwise complex sequence, say, or otherwise normally if it is a real number. So what we can do is we can say that this is an even part of the sequence. So now similarly we also have odd part of the even sequence, and if the sequence is a complex number, then we will say the conjugate anti-Semitic. This x0n is normally that also known as conjugate anti-symmetric part of xn. So now its Fourier transform is actually here jxi e to the power j omega. So this is actually this portion is the imaginary part, and multiplied by this imaginary identity, this j, that Euler identity, that j. And here this denotes that xr, we know this is the real part, and this part is the imaginary part. So here you can do it. If you take the inverse Fourier transform, you will be getting this. And from here, if you take inverse Fourier transform, from this part, if you take inverse Fourier transform, we'll be getting this. So this property is already, well known to any person who is working in actually signal processing. But normally we didn't deal this one separately. Actually, we consider them all together. So here, what we'll be dealing is we'll be, using this separately. This portion, and then we will try to get from these to from this, yeah, otherwise from this to this, or otherwise if we get this, and how do we get this DTFT of the signal xn. So that's the point. So here the introduction here is, as I said, we will exploit the odd and even sequence of the given sequence xn here. So here xn, actually this xn can be expressed as even part of the sequence as well plus the odd part of the sequence. So now by definition, this even part of the sequence is given by this expression xn plus mirror image of xn divided by 2. So the signal that we get is what we call as, here also another term is there, complex, the conjugate symmetric, if this xn is a complex number. But here by definition, we said here any sequence. So this expression can also be applied to real sequence, yeah, otherwise in complex sequence also. So here it is the odd part. So odd part, how do we get is xn minus mirror image of xn divided by 2. So that's that part of the sequence. If xn is a complex, then this is what we call as conjugate antisymmetric. Or if this is a real sequence, then we say this is the odd part of xn. So if this is known, so what do we do is we are going to exploit this expression, actually this property. So if this is given like this equation 1, from equation 1, say we have equation 2 and 3. So from here you see it here, looking at this, we will know. We are also going to exploit another, or otherwise we're going to put one more condition here. Say, now suppose this xn is a causal sequence. That is, causal sequence means xn is 0 when n is less than 0. And its value is non-zero when n is greater than or equal to 0. And in the case of mirror image of this, it will be just the opposite, right? Then if this satisfies, then it is possible to recover xn from xen completely, or otherwise it can be recovered from the odd sequence that, otherwise we say the conjugate antisymmetric x naught n for the other samples, but not for in the case of say odd sequence. Let's say here actually in the case of odd sequence, this when n is equal to 0, this odd sequence is going to be 0. So what we say here is xn can be completely recovered when n is not equal to 0, because when n is equal to 0, this x0n would give us 0 value. So that's the issue. So what we're saying is that even if, say, without going into the Fourier form, so even in the time domain also, if you have even sequence, we can recover this xn, or otherwise we have odd sequence here. Yeah, otherwise conjugate antisymmetric. For n is not equal to 0, we can easily recover xn. So that is what it is. So that one we can easily verify. Here it is a little bit difficult to visualize, but anyway we will see it in the diagram form. This mathematical sometimes this mathematics expression, sometimes it is difficult to visualize, but anyway I have a diagram after this, so I'll show you how can we do that. So here the non-zero portion of xn and these do not overlap. Yeah, okay, anyway, no problem. So if this is true, then from here what we can do is we can get that here we can get an expression here, xn is equal to, that means this recovery part. So xn is equal to twice of xen multiplied by un minus xe0 multiplied by delta n. And say if we want to recover this xn from the odd part, yeah, otherwise conjugate antisymmetric part of xn, then in that case this is the expression. So this expression is difficult to visualize now from the mathematical expression. So we have an equation here. We have a diagram here. Is there any question so far? If there is any question, please interrupt me. So never, my pace of speaking is it okay? Or am I speaking
Yes, sir.
too fast? People used to say that I speak very fast. I don't know. Okay, so we have xn here. So let us verify this expression, these two expressions. So we have this xn here. So if we take mirror image of this, so this is the signal in graphical way. So xn is given, and if we take mirror image, we get this. Now, what this equation, what this says, see now here, what this expression, the first expression, what does it say is, now you add these two, right? What it states, twice of xen multiplied by un and minus xe0 multiplied by delta n. Delta L delta L is nothing but 1 only when n is equal to 0. So here actually it is just multiplies 1, and it is to ensure that other samples are not associated with this term. So here you see it, if you multiply this by 2, right, and then again remove this portion, that means multiply this signal by 2 and multiplied by un, that means unit step sequence, we still get this. Only thing is that these amplitudes are all double up, right? Okay, in case if it is difficult to visualize, I think we have here. Let's see here, this expression actually, yeah, this one. So proof of this here, now you just, okay, add these two and divide by 2. So what do we have is this. This and this, we add it and divide by 2. So we have this. So this is what we call as this even sequence, otherwise conjugate symmetric. If xn is a complex number, or if xn is a real number, then this is what we call as even sequence. So even sequence is obtained like this, and for odd sequence, this minus this divided by 2 would give us the odd sequence. This is the odd sequence. That is why if xn is a complex number, we say this is conjugate anti-symmetric. Here in the case of this, here it is conjugate actually symmetric around this y-axis. Here it is conjugate anti-symmetric around the x-axis. Now after getting this, you see it now here, this you just multiplied by 2 here in this even sequence to get this first expression, to prove this first expression. I think this expression is okay. This expression is okay. This expression is understood from this diagram, right? This plus this divided by 2, right? And so it is understood from this diagram. So this is why if xn is a complex number, then I mean the complex sequence, then we say this is a complex symmetric. It is symmetric around y-axis. Now from here, if we want to recover from this xen, we want to recover this xn, then what should we do is, see now here it has been, because it was divided by 2. This plus this divided by 2. So that means this magnitude just reduced to half. Right, except this when n is equal to 0. This n is equal to 0, this sample has the same value here also, here also, here also, right? Because this plus this divided by 2 gives the same value. So this value, this value, this value, they are all same. And the other samples, it was reduced to half, right? Because here, if you see it, this corresponding sample value is 0. So this plus 0 divided by 2 would be just reduced to half. That is how we get this. Now, we want to get this. So if we want to get this, what should we do? We just have to multiply to this signal, xen, we just have to multiply it by 2. So when we multiply it by 2, what do? All these samples has been, we get it. Now, what we have to do is, which was reduced to half has been now doubled up. If it is doubled up, so it is equal to these samples, except when n is equal to 0. When n is equal to 0, this values becomes double, right? So that is why here, if you see it here, That is why here when xe0 minus xe0 is there, because since it was developed by that multiplication, multiplication by a factor of 2 to xen, so this has to be developed, so this will be double. Here this x0 would be, whatever that we have, that value would be double. So just to remove that, so we just have to subtract by xe0, this original sample. So when this subtracted by xe0, so it would be reduced to the actual original sample value when n is equal to 0. Now when this side is also double up, so we get this value, and then this when n is equal to 0, so that sample value also has been taken care of. And this side is also double up, but it goes this way and extended, and then reduce it in this way. But what should we do? Because this wasn't there in the original, so for that reason, what we do is in the first term here, it is multiplied by unit step sequence un. So when we multiply by unit step sequence, so this would be definitely unit step sequence. By definition, we know un is equal to 1 when n is greater than equal to 0, and un is equal to 0 when n is less than 0. So when n is less than 0, all un has a 0 sample value. So 0 multiplied by any sample value would give us 0. So that's why we can easily recover this xn from xen by just multiplying by 2 multiplied by again by a unit step sequence, and minus x0 n multiplied by delta n we give, because just to ensure that it only picks up when n is equal to 0. So I think this equation is also understood now. So in the similar way, we can actually get this expression, recovery expression of this xn from here, right? So in that case, see, same thing we have to do. What we should do, we should just multiply it by 2 again here as we did earlier, and by just multiplying it, this sample should be double up and would be equal to this, and this side also would be double up and will not be equal to this. So for that reason, when x0n is multiplied by 2i's, then in that case we also have to multiply it by another unit step sequence, so that this portion has been filtered out. So when we filter out, actually this xn is not equal to 2i's of x0n multiplied by un, right? It is not equal, because here this sample when n is equal to 0 is not there. So we need to add this sequence here. So we have to have some sort of a device or mechanism that we provide the sample value when n is equal to 0. That is why in the definition, if you see it here when I said here, it says that xn, all the sample of xn would be recovered from x0n except for n is equal to 0. So what do we do is, in that case, we have no other choice. So if we have the original, x0 value is provided, then fine, no problem, you just add up there. If it is not provided, then we have to do some sort of mechanism, or we have to do something so that we at least get the expression of we at least get the value of x0, right? We have to do something. So there are examples. I'll show you how we do that. There is one example I have given. Yeah, otherwise normally some conditions are provided in the problem, and from there we can easily get the value of x0, the sample value when n is equal to 0. So is there any question so far? If this is understood, then my whole job is over. We will see examples and see it. How can we recover, or one part of the Fourier transform from the other parts?
Electronics and others, if you want to put some questions, you can put to sir.
Please. Okay, thank you. There is no query so far. So if this is understood, my job is over. So we'll see the examples now. So here there is also one note here. Say note that xn is completely determined by this, but on the other hand, here I'm just putting a caution kind of thing. For completely recovering this xn from xen is easy. It is easily understood. But however, for recovering xn from x0n, actually here we need the knowledge of this x00, or otherwise it is equal to 0. Yeah, otherwise we have to have something, because when n is equal to 0, this x0 is equal to 0. So that condition we should keep in mind. Okay. So this is the complete, actually the introduction or the complete theory that we would be using. Now in the Fourier transform part, so let's see something what I have here. Okay, here it's also more or less hinting what I have said there in the time domain. So here in frequency domain, that is also some part of a little bit of explanation that I have given here. So xn has been segregated into real part and the imaginary part that we know. So up to this is understood. So we know that if xn is real, then this then the sequence, this real part of the Fourier transform DTFT. Okay, yeah, real part of the Fourier transform is nothing but the Fourier transform of xn. That though I think I have already said at the beginning, actually, two properties I have shown you, the Fourier transform properties. Okay, there is nothing wrong. So then, yeah, therefore, then for a causal, stable, and real valued sequence, real part of the DTFT is completely, okay, real part of the DTFT completely determines this DTFT of xn, right? Provided this portion is already given. So that means what I'm saying here is, if this is given, if this is known to us, then we can completely recover this from this. That is what it says. Sometimes it is a little bit difficult to understand when we write in Word, because I just put one condition here, causal, for a causal sequence. So here, if you remember correctly, here I have considered a causal sequence. However, this expression is valid for any type of sequence. But for our analysis purpose, or for this purpose, recovering from one part to another part, where we are considering Z, or maybe this equation is valid only for when this xn is a causal sequence. So this is actually without mathematical analytics. If we use a mathematical analytics, then let it be any type, this xn be any type of sequence, whether it is causal or non-causal, you can straight away get the this real part of the DTFT straight away from this. Yeah, otherwise this one, this imaginary part of the DTFT, we can straight away get it from there. There is a relation called discrete here, Hilbert transform. That is what we normally use it in signal processing. That is the term that we use it. So relation between real part and the imaginary part of this Fourier transform is what we call as discrete Hilbert transform relationships. So in mathematical analytics, normally in the field of mathematics, they call it Poisson's formula. But anyway, we are not doing mathematical analytics here, so we don't need to worry about that. That's a long derivation there, and we can easily do it using Cauchy-Riemann integral. Anyway, we'll not go into that mathematical analytics. So here we will go the simple and easy way, provided we have to consider that this xn is a causal, real valued causal sequence. So here are the steps, how to do it. So here I said, yeah, algorithm and steps. So here are a few steps that we have to follow. First one is determine this xen by taking, see here what I said at the beginning is, it can be in two ways, but let us start with the easy part. So let's say this real part of the DTFT is given, right? So this DTFT is given because now it was easy, even in the diagram, in that signal diagram also we have seen that when for the even sequence, it is easy to recover this xn from even sequence, because in the odd sequence there is one sample where n is equal to 0, so we had an issue. So similarly, but that can easily be dealt with, that I told you. So here we will go with the easy part, and once we understand that one clearly, then we can go the other one. So here algorithm has been given for this. So we assume here that this real part of the DTFT is given. So once from this real part of the DTFT, if we take inverse Fourier transform, then we get the xen. Then next, what we should do, we have to use those two equations, these two equations. We have to use these two equations to recover xn, right? Once you know this xen, then we can easily recover this. See now here, there is nothing, right? It's simple. because on the right hand side, if you see, it is only xen. So once the xen is recovered, we can recover this xn easily, right? Okay. Here is also the expression. I thought expression is not there. So using this expression, we can easily recover this xn. Once the xn is recovered, what we can do is you take Fourier transform on it. We'll be getting this DTFT of xn. Once we get the DTFT of xn, then this can be expressed, broken down into real part and the imaginary part. So this value would be equal to what was given in the problem. So what would be new is this term. So this term is nothing but the real part of this. So that means these 3 steps, what does it say is this was given and we can easily obtain this. Am I clear to you? These are all the background and the theories of today's talk. Now we can, if you understood this clearly, if you understand my explanation clearly, then we can do that. We can go to the example. Any question here? Okay, no queries, nothing. Easy learning is understood. Okay, so it looks like it is easy to understand and no issue. Thank you so much. So let's see the example. So now here in the problem, this real part is given here, and the real part is equal to cosine omega, right? So cosine omega is given, and we want to recover xn. We want to recover this xn, right? That was the second step which was given there. So what we should do is we will be now this cosine omega we can express in the exponential complex exponential using Euler identity, right? Cosine omega as per the Euler's identity is e to the power j omega plus e to the power minus j omega divided by 2, right? This is what Euler identity says. So we are expressing this this cosine function cos omega into complex exponential. Now we're just segregating these two terms, this one. So when we segregate, it's easy. So we have segregated. Now what is the next step? So once we this is given and it has been expressed in complex exponential. Now the next step is to take the inverse Fourier transform, right? We have to take the inverse DTFT. So when we take inverse DTFT, we know the inverse DTFT inverse DTFT of real part of xn, real part of the DTFT of xn is nothing but xen, right? That's what I said earlier. So now you see here this exponential function we have. So this 1 by 2 is the constant, so it has come out. So when we apply Fourier transform definition, if you remember correctly, sum of when n goes from minus infinity to plus infinity and the xn, that means here it is xn, here is e to the power j omega multiplied by e to the power minus j omega n. When you do that, when you sum up, you will be getting only one function, one delta function, so one value. So here, I think I don't need to write this function, or you understand this. How do we do? Or otherwise, actually, it's a basic thing only. So the complex exponential, when you take the inverse Fourier transform, so it is nothing but an impulse. I think you understood this. So if it is j omega, then you have a +1, and if it is minus omega, you will have a delayed version on the pulse, -1. And if you have 2 here, you will be getting delayed by 2 units. And if it is e to the power j omega 2 omega, then you will be getting advance of by a factor of 2. I think this one too, you understand this. These are all basics of Fourier transform. Any question here? I think this is the basic. I think you might have understood, or maybe if you have any issue, then I can do that by just applying the Fourier transform definition. We can do that. E to the power minus j omega n plus this. So it would be, this portion would give you this advance here because it is plus, because that, base is same, so the power would be added. So when power is added, minus j omega n plus j omega, so you take that j common, then you will be having this. So that summation actually is going to give you a value 1 when n is equal to what? N is equal to minus 1, right? In the case of this, and in the case of this, when n is equal to plus 1, right? So you'll be getting only one value there from this complex function. So when we take inverse Fourier transform, this is what we get. And when we take Fourier transform on this, no, inverse Fourier transform on this is what we get. So once we get this, then using the definition or the relation that was given earlier, this relation, right? This relation, we have seen it from the diagram. So using this relation, what we can do is, see, now you put it here, xen to multiply, to multiply by this xen, this whole thing, you put it there, and then multiplied by this unit step sequence, minus here in this expression, you just let it n is equal to 0. When n is equal to 0, you will be getting xe0. Here, when it is 0, what do we get? This will be 0, this will be 0, because this delta function here, this delta function delta n plus 1 would be equal to 1 when n is equal to minus 1. In the case of this, when n is equal to plus 1. So when n is, but in this expression, when we put n is equal to 0, you see here delta function, here delta 1 and here delta minus 1. Actually, delta minus 1 is 0 and delta 1 is also 0. Delta n is equal to 1 when n is equal to 0, right? So this xe0 is going to be 0. So 0 multiplied by this delta function is going to give us again 0. So this term will be out. This term will be out. Then again in this term, right? This term which is these subterms, right? These subterms and these subterms. Here it is going to be multiplied by this unit step sequence. So when this function, right, this combined function is multiplied by this sample will go away, because this sample is on the left hand side of the xy plane, and here this is on the right hand side. That means this is a delayed sample and this is an advanced function, advanced sample. Advanced sample is on the left hand side and the delayed samples are on the right hand side, right? So when it is multiplied by un, definitely this term is also going to go away. Is it clear to you what I am trying to say? In fact, I'm struggling to, I'm struggling to make you convince what I'm saying actually. So if there is any question, please. Is that okay? I think everyone understood. Satabrata Singha says that there is no problem. Okay, easy learning says that I should repeat again. Okay, I'll repeat. So easy learning wants me to repeat it, so let me repeat again. Here, we have this one, no issue. Otherwise, you can use your microphone also, because here every time if I have to see your comment, what I have to do is I have to minimize the screen and see your comment. But if you speak, then I can listen to you, because when I maximize, when I put my slide in full screen, I actually cannot see what you are writing there in the chat box. So easy learning, I think you understand what I'm explaining here. Real part of the Fourier transform is given, and which is cos omega. And this cos omega expression is written in complex exponential using Euler identity, right? Euler identity. So this is what we get, and this has been expanded this way for our easy understanding. And again, in fact, what we're doing here is we're just preparing to take inverse discrete time Fourier transform. That's why. So inverse discrete time Fourier transform from a complex exponential is quite easy. When it is 0, so when it is 1, then you will be getting delta n. When it is exponentially for j omega, this is actually will give us the delay, right? Delay. This is delay or advance. If it is positive, it will be advance. If it is negative, it will be delay, right? N minus 1 is the delay, right? Delayed sample by a factor of 1. Here, this n plus 1, actually, it says that this is a delayed function, advanced function of, by a advanced sample by a factor of 1, right? That we know. So the advance means this sample would be on the right hand side of the origin when n is equal to 0, and this would be on the this would be on the left hand side of the origin, and this sample would be on the right hand side of the origin when n is equal to 0, right, in xy plane. Okay, I think this one is understood. DTFT is understood. Once DTFT is understood, so this expression was also, I make you understand through diagram, right? Signal diagrams. So now here in this expression, we're going to put this, right? So xen is known to us, so we're going to put this here. So when we put here, I am just using a basic thing. I have not skipped any steps. So here xen is replaced by this, right? So that's what I put here. And then minus here and xe0. And xe0, when you put n is equal to 0 here in this expression, right? When n is equal to 0, so xe0 is equal to 1 by 2 delta 1 plus 1 by 2 delta minus 1. That is what we get here, right? So delta 1 is the sample on the delta 1 is a sample on the right hand side in the xy plane, and here this index, right? This function, delta function here, index is n is equal to 1. Actually, when n is equal to 1, delta function gives us the zero magnitude, right? So this term would be 0 because delta 1 is 0. So here this is a delta this is a sample given from a delta function, and this sample is just looking at the index here. Say index here is -1, right? So that means it is on the left hand side of the xy plane, right? So on the left hand side, if the sample lies, and here you see it is not n is equal to 0, right? Here n is equal to -1. So this delta function would give us a 0 value, right? 0 multiplied by half is 0. So this term, basically these two terms actually will go away, right? This will be 0, this will be 0. So this will be 0. Again, 0 multiplied by delta function would give us 0. So this term is gone, complete. Now coming back to this here. This sample, actually this delta n plus 1 sample is on the left hand side, and it is an advanced sample, and this is a delayed sample, right? Delayed by a factor of 1, right, on the right hand side. So when these two samples are together and it is multiplied by a unit step sequence, right? So unit step sequence, by definition, we know un is equal to 1 when n is greater than equal to 0, and when this un is equal to 0 when n is less than 0. So here in this case, n is -1, right? So when n is -1, then only this delta function n plus 1 gives us 1 value, right? So that means when n is -1 means it is on the right hand side. This sample is on the this sample is on the left hand side. So this sample on the left hand side will be definitely go away with the when we multiply with the samples of this unit step sequence, right? Unit step sequence, if you know it, it is like 0 0 when n 0 0 would be there. Sample values, all the sample values on the negative sides are zeros, and all the sample values starting from n is equal to 0 and towards the positive side, they are all value with a unit value, right? All the sample values are equal to 1, right? So 1 multiplied by anything is always anything. Okay, so 0 multiplied by anything is always 0. So this anything multiplied by 0, because 0 will come from here, right? 0 multiplied by this will go 0, will give us 0, but this one is going to be non-zero. Okay, so when this is, so you see actually it is multiplied by 1. So here it is multiplied by 0 because of this un. So what we have, this term is also gone. This complete thing is also gone. This is also gone. So what is left with us is only this, right? Here now 1 by 2 multiplied by 2 gives us 1. So what is left to us is only delta n minus 1. Okay. So it is only delta n minus 1. So that means xn is equal to delta n. Okay. So in the problem it says that real part is given and which is equal to cosine omega. Then the original sequence is found out to be delta n minus 1. Any question here? Okay, thank you. Easy learning. What about others? Is there any question? No question. So we can see the next one. You can see the next one. So in the next one, what we do is instead of having cos omega, so I have added one more value here, 1 plus cos twice omega. And we would like to, yeah, from here also it is easy actually. I'm just modified here. If you take, Fourier transform here, we'll be getting the DTFT of this real part of the DTFT, right? So here we are going further. Up to here, we are just finding out the original sequence. After this original sequence, if you take actually the Fourier transform here, DTFT, we'll be getting this one, right? X is equal to j omega, right? DTFT of the DTFT of xn. So that is what it is. So we are going one more steps beyond. Okay. So the whole process is similar to what we just saw in example 1 actually. So we'll just proceed in the similar way. So we write this cosine function into complex exponential functions using Euler identity. Then what we do is then after that what we do is we take inverse Fourier transform on it, right? Inverse DTFT. When we take inverse DTFT, so this would give us xen, and this one gives us delta n, and this one will give us 1 by 2 delta n plus 2. This will give us that I told you this portion, this function, right? This coefficients here in the power coefficient would give us the delayed factor here. So this is what we get. So I think this one is easy. Inverse DTFT of the real part of the DTFT of xn is easy here. So we get this. Once we get this, use the similar procedure. So similar procedure was to use this expression, because what we get is here we get the even part of the sequence. Yeah, otherwise we should say the complex conjugate symmetric sequence of xn we get. So from there you try to get the complex sequence, original sequence xn. So this is what we get. You please look into it. If you have any issue, let me know. I think I have written this equation straight. Unlike the detail detail explanation I have not done here. I just put it. So if you have any issue, please let me know on this equation. Okay. If that is understood, then this problem also is over. Okay, no problem. Since you all have decided not to speak to me, so I have to minimize my screen and see what you have written there. No problem. Thank you.
You can speak up.
It's okay. So, Sonivar, any issue from your end? Is my explanation loud and clear?
Those who are from electronics background, for them, I think it will not be a problem. Or
electrical also, I think, should not have a problem. They must be using this in signal system and mathematics teacher. that he might be thinking, because this is not analytic. What we are doing is, because the engineering, we always use the application point of view. So we are using applied mathematics here.
I see a lot of CS guys missing today.
Okay.
Yesterday there were a lot of CS guys. Today
Okay.
maximum CS guys are missing.
Oh, so we all are familiar with the other part. So here I am doing on the other part, and I'm also not sure whether you have seen this earlier or not.
No, one Dr. Abhishek Das is here. He's from Alia University. He is there, but maximum CS guys are missing.
Okay, no problem. So if there is any question or if there is anything, please interrupt me anytime.
Yes, you can speak up in the microphone. Sir will be free to tell, because it is troublesome for sir to minimize and see the chat box.
So if there is no issue on this expression, how we get this using this expression. So what we have here is the finally, if you take, if we take Fourier transform on this, so finally this is what we get. Fourier transform of delta n is 1. Fourier transform of this delta n minus 1 is e to the power minus j twice omega that we have seen earlier, right here. So it is going back from here to here or from here to there. That is what we do here, right? So we get the complete, now real part was given there in the problem, and we get the complete for a DTFT of xn here. This is how we arrive at. So if we want to express this in sine cosine function as it was given in the problem, so this is what we have. So this exponential function we can express in sine cosine function, again using Euler identity. Euler identity. So this is what we get. So this portion 1 plus cos twice omega is what was given in the problem. So this portion is the real part and imaginary part is this. So from here we can conclude that even if it is not asked in the problem, in case if this is the same part which was given in the problem, and if we are asked to find out the imaginary part, because the real part is given and we are asked to find out the other part of DTFT, that is imaginary part, then we can easily do it. So here it is the real part and we have the imaginary part here. So the imaginary part of this DTFT is minus sine twice omega. Because this DTFT, when we break down into real and imaginary, this is the expression, right? This expression is known to us. This is what it is. And from here, comparing this side of the expression and this side of the expression, so imaginary part of the DTFT is obtained as minus sine twice omega. So example 2 is also over. So we are left with one more example, that is here. Real part is given. Another function we have I have taken up here, real part is given, and we are asked to find out the imaginary part. So it's the same thing. Here what we have to do is we have to start from here and go till this. Earlier what we do is, as the problem asks, we could have stopped there. Now the next problem says that from here we started and then we have to end it there, right? Real part is given and we are asked to find out the imaginary part. So same process. Here we write in exponential again from here. It's quite easy. Express this cosine function into complex exponential. Then we take inverse DTFT. So when we take inverse DTFT, that is what we get, right? So once we get this expression, then use that expression that we had earlier, twice xen multiplied by un minus xe0 multiplied by delta n. We use this function. And from there, it is easily we can say that xn is equal to delta twice delta n minus twice a delta n minus 1. So we get the sequence, complete sequence. The real part was given, we get the complete sequence. Once we get the complete sequence, what to do next, we all know, as per the algorithm that I have listed out earlier. So we have to take DTFT here. So when we take DTFT, then this is what we get. When we take DTFT here, so take DTFT here, so it would be 2 minus twice a, and in e to the power minus j omega, because here the delay factor is 1 minus 1 here, yeah, minus actually 1, delay factor is 1 here, so it would be e to the power minus j omega. So this one again we write in sine and cosine form. This is what we get. So the real part was what was given in the problem, and the imaginary part is what we have here. So the imaginary part here is twice a sine omega. So this is what we get. So real part was given in the problem, and we found out the imaginary part of the DTFT of xn. Any question? No question. So all
No, sir.
so the teachers are also like students. No, in the class and many students don't answer, and that is quite frustrating also, right? But anyway, we all are teachers and we all understand what actually it is. So I think I have already taken 1 hour time, right? So I'll not take. So Nevar, how much time you have given me?
So we have given 1 hour.
Okay, 1 hour is almost over. So this is the last one. Okay.
Sir, you can extend also, no problem.
Okay. So maybe about 15 minutes I'll extend.
Sure, sir, no problem.
We have one last problem. So here in this problem, earlier so far in the last 3 examples, real part of the DTFT were given, right? Real part of the DTFT was given. So in this problem, instead of real part of the DTFT, here imaginary part of the DTFT is given, and we are asked to find out the sequence xn, right? So this is different from the earlier 3 examples. So here, but the process, as I told you earlier, process remains the same. Only thing is that in the middle, in the I think in the second algorithm, in the second step, what we should do is, instead of using that even function expression, we should use odd function expression. But again, we have a one hiccup here. How do we recover the samples when n is equal to 0? So that issue is there. So that is actually the thing. So once we get the expression, we will get to know how we can, see, and then how we can do some walk around and then get the result. So here, here now this sine function. This sine function has been expressed in the complex exponentials using Euler identity. Now, if we take inverse Fourier transform of this, it is nothing but the XON conjugate antisymmetric. Yeah, otherwise we should say the odd part of the sequence. So this is what it is. Here, this will give us delay, right? This is what it is. Actually, here all j has been gone. You will see here one thing earlier in the first expression in the first slide. x0n is DTFT of x0n is j imaginary part of the DTFT of xn, right? J is there. So all this j will go away. All this j, actually, we can take it this side, and we can comfortably take the, we can comfortably do what we did earlier in the last 3 examples. I think this portion is understood to you. Please do not confuse. You must be wondering here, all j, this imaginary, this function is missing here. So it is basically because of this. DTFT of this is j imaginary part of DTFT of xn, actually. So j is already there. So all this j can be taken out and then put it on the left hand side, so that we can comfortably take 1/2 this one, as we did earlier in the earlier examples. So here the value, the power is positive, so we would be having the advance of 1. Here it is minus, so we would have a delay of factor of 1. Here it is 2, so it would be advance 2. Here it is minus 2, it would be delayed by a factor of 2. So the earlier this coefficient signs would remain same. except the functions, right? So when we take DTFT of this, so we get this. I think this portion is understood to us. One thing you have to keep in mind is that x0n, DTFT of x0n is equal to j imaginary part of DTFT of xn. Having said that, now the next step is to recover the sequence xn, right? So for recovering sequence xn, we have to use that conjugate antisymmetric expression. This expression, we have to use this expression. So here, this expression that we use in the same explanation that I did earlier is the same thing. Only thing is that this, because this all this sequence remains the same, all these functions remains the same as I explained earlier. So if you simplify this, what we get is this, right? So here, actually, this portion x0 is not given here in the problem. So since x0 is not given here in the problem, we have to look into this expression and see it. Now here in this expression, you see here when n is equal to 0 is what actually x0 is. So when n is equal to 0, you will see this will be 0. This will also be 0. So this x0 is equal to x0. So that means you take any value of x0, you take any value of x0, it will always, can be expressed or would bring to this, actually this expression. This expression would always be a correct solution. Whatever value that you put, x0 is equal to 2, x0 is equal to 3, whatever it is, you take it, it would always, satisfy this expression. Right? So for simplicity, we take the minimum value. So when x0 is equal to 0, so that gives us this portion will be out. So this minus this would give us xn. Right? Once you get xn, we know you take Fourier transform on this, you can easily recover real part of DTFT of xn when imaginary part is given. That can be extended. So that's all about this example. If there is any question, please let me know. If there is no any question, then that is all about I have to say for you today. And the books that I use is this book. So the teachers from electronics department would know this book, Discrete Time Signal Processing. And I also believe that the teachers from IT, CSE, and electrical engineering, if they have taken up those signal processing subject, yeah, otherwise digital signal processing subject, you might have used this book. This book is very popular. Oppenheim and Schaeffer book. And the title of the book is Discrete Time Signal Processing. And whatever that I had been discussing here is given in the in this book at chapter number 12, right? Chapter number 12 of this book. So this book has about, I think, 13 chapters. So last but one chapters. And I told you at the beginning also, this relation actually, we can, without going through all this mathematical thing, all this applied mathematics, these ideas, we can straight away get real part of the DTFT of xn if this imaginary part is known to us. Yeah, otherwise real part is known to us. We can straight away get the other part. That relation is what we call as, I repeat again, that relation is what we call as discrete Hilbert transform relationship. So in mathematical, analytical mathematics, that is called Poisson's formula. So using Cauchy-Riemann integral, so we can get those relations also. So in that case, we don't need to go through all this, and we can straight away get those expressions, otherwise values. But that is the mathematical part here. No, mathematical analytic part here. We are not using mathematical analytic part. That's all from my side. If there is any question, please let me know. And Soniva, over to you.
So students, do you have any question?
No, sir, thank you. This is quite a revision for us. Thank you for the session.
Welcome. If there is any question, please let me know. Over to you, Sonibar, if there is no any question.
Electronics guys. And from mathematics, I can see Rakhal here. Anybody else from physics? They are not having any query.
Okay. But I simplified as much as possible. So, but even then, if there is any issue, please let me know.
Yes, sir is very much available in his mail. I can share the mail ID in case you are having any queries. So I think there is no question. So I would like to thank the speaker. Sir, thank you very much for sharing your knowledge with us and for the mainly me being from electronics background. It's I know that the electronics guys or those who are working on signal processing, for them it is very much beneficial. Uh, I don't know about physics and mathematics. A few of them had shown interest initially. So, and I would like to thank you, sir, for being with us and sparing your valuable time to share your knowledge with us. Thank you very
You're
much,
most
sir.
welcome, sir. And it's my pleasure to be with you all today afternoon. And my details, or if there is any query in future, you can always reach out to me. My email IDs are also given in our university website, in the department page. If you go through it, so you can get details there also. So, Nivar sir, anything else, or we can close this?
Yes, sir. We can close off, sir. Thank you very much, sir.
Welcome.
Today we'll not be having the second session. We'll be having that tomorrow. We'll be having 3 sessions instead. So the participants tomorrow will have 1:30, 3 and 4:30, 3 sessions instead of today only. Sir's lecture, the other lecture of 4:30 p.m. we had to shift it tomorrow. So we'll be closing today. Today only we were having sir's lecture. Maybe due to that also many participants, after getting the mail that 4:30 lecture was cancelled.
Okay. Okay. Okay, then thanks a lot. So can I leave the
Yes, sir. Yes, sir. Thank you, sir.
meeting now? Okay, thanks a lot. Bye. Take care.
Yes.
Participants will join tomorrow at 1:30 because today's 4:30 lecture will be rescheduled tomorrow at 1:30. So tomorrow we have 3 sessions, one at 1:30, one at 3 and one at 4:30. We have kept lectures of 1 hour with discussion and a bit of buffer time so that the next speaker doesn't have to wait. So today, due to unavoidable circumstances, the other speaker also is a dean, so he had to cancel it. So thank you very much.
Thank you, sir.